we present MoNeRF, a novel approach for fast, non-rigid radiance field reconstruction from monocularized data. For a given non-rigidly deforming scene, our method is capable of real-time novel view synthesis after only 7 minutes of optimization. As input, it only requires a set of monocular images with varying viewing angles. We start by recording and segmenting a dynamic scene from multiple camera views. To train our model, we then use the recently introduced DNeRF data setup, which only contains a single randomly sampled monocular view per time frame. We train our model end-to-end using differentiable volume rendering. First, we cast a ray from a training camera view and sample discrete positions along the ray. The sample position and corresponding camera timestamp are then passed to a deformation component that estimates a three-dimensional offset vector into a canonical scene representation. Our factorization-based deformation component disentangles temporal and spatial information by using two individual MLP components. These networks estimate high-dimensional feature vectors for the position and timestamp, which are then linearly combined to obtain the final offset vector. The transformed positional sample is then fed to a hash-encoded neural radiance field that models the scene in a canonical space. Here, we sample features from a multi-resolution hash grid using trilinear interpolation. These features are then processed by two shallow MLPs that estimate the density and color at the discrete input position. We obtain the final pixel color by estimating the discrete integral over all samples. By comparing the predicted and ground truth pixel colors, we can iteratively update our model parameters to reconstruct the scene deformation and appearance. Here we show results on the DNeRF dataset, which contains 8 synthetic scenes recorded by a monocular teleporting camera. In this setup, our method reconstructs a radiance field of the full object in only 7 minutes and renders high-quality novel views in real time. We compare our results to recent benchmark approaches using a static novel camera view. In direct comparison to DNeRF and RNeRF, our method produces more detailed results in a substantially shorter training time. The static test camera position further reveals that the motion reconstructed by our method is more stable and more temporally consistent due to our explicit scene representation and smooth temporal input encoding. Even compared to the recent state-of-the-art approach, TinyVox, our method preserves finer details, trains faster, and achieves real-time performance during rendering. To test our method on real-world scenes, we record a new dataset recreating the DNeRF setup. For this purpose, we record a total of 12 scenes using a large-scale multi-view camera setup. Our scenes feature human motion and general object interaction in various challenging scenarios, including self-occlusion, loosely swinging cloth, and high-frequency texture. To emulate the teleporting monocular camera of the DNeRF dataset, we monocularize the recorded multiview data by randomly sampling an image from a single camera for every time frame, resulting in an efficient and compact representation. Similar to the synthetic case, our method enables high-quality novel view synthesis from real-world monocularized data and is significantly faster and more stable than the related DNeRF and NR-NeRF approaches. The direct comparison to the recent TinyVox further reveals that our method is not only faster in terms of training and rendering time, but is also more robust to natural inaccuracies of real-world recordings. Besides fast training, our method achieves real-time frame rates that enable users to freely explore the reconstructed scenes and deformations as shown here. Thanks for watching.